I'm sorry? Probably not. So work. We talked about this a little bit ago. So a quick review. Work is equal to, in general, the magnitude of a force vector times the magnitude of a distance vector times the cosine of the angle that's between those two vectors. So, for example, if this is our force vector, and so the force is applied in that direction, but the displacement or distance traveled is along that direction, then there is some angle between those two vectors. And the actual work being done is equal to the component of the force vector that is in the direction of the displacement. So in the language of pre-calculus that many of you are in, you're going to map the force vector onto the displacement vector. And in doing so, this mapping, this thing right here, is obviously the force vector magnitude times the cosine of the angle, because that's the adjacent leg. So F cosine theta is the mapping of the force vector onto the displacement vector. So that's the math of it when you get to this in your pre-calculus class. As far as physics is concerned, we just need to know that it's the magnitude of the force times the magnitude of the distance or displacement times the cosine of the angle between them. Now this is what's known as a scalar product. So scalar product is another way of saying dot product. So in general, if we have some vector A, and let's say that's let's say it's just two-dimensional right now, so it has an x component and some y component, so a sub x in the x direction, which we use an I vector for sometimes, and the y component, a sub y, in the y direction, so which we'll use j. Sometimes they put little roofs on top of these things. I usually use x roof and y roof instead of I and j, but in math you're probably going to run across I and j. And then you've got some vector b, and it's going to have its own x component and its own y component. In component form, they may be written like this instead, using angle brackets to indicate it's a vector. The x component and the y component of vector A, the x component and the y component of vector B, and to find the scalar or dot product, mathematically, if you have your vectors in component form, is a very simple thing to do. A dot B is equal to the product of all the x components, so this would be ax times bx, plus the product of the y components, so ay times by, and that's it. and it's a number. You get a number out of it. Hence, it being a scalar. So work is a scalar. It is not a vector. So back up here now, so work equals, I've already got that. So this is one way in math that you can find the angle between two vectors. Yep?
Another question. What is the difference between a scalar and a vector?
Okay, we're going to go way back to August. A vector is a quantity that has both magnitude and direction. A scalar only has magnitude. So, this is one way that you can actually find the angle between two vectors, especially if you have them in component form. If not, you can always break them into component form. We know that the x component is the magnitude times the cosine of some theta, where theta is the angle from the positive x-axis to wherever the vector goes, and so on. So, let's do an example. Something basic and straightforward. Okay. So we have some mass, a crate maybe. It's resting on a floor. We could have friction or not, doesn't matter. Let's say there is a force that's being applied in the direction of the motion, because this crate is going to move that distance d. So the work being done by force F, since the distance that it travels, the distance vector and the force vector are in the same direction, the angle between them would be 0. Good. And the cosine of 0 is 1. So we could say, oh, well, we take the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. So in this case, it's simply the magnitude of the force times the magnitude of the distance, because the cosine of 0 is 1. If, however, the force vector is not applied in the same direction, for example, we have our crate of mass m, and we're pulling along a rope that is some angle theta above the horizontal. So we're applying the force at an angle other than in the direction of the displacement, because this thing is going to be dragged, so this distance, and so that's the direction of the distance or displacement vector, the same as horizontal. So in this case, the work will equal the magnitude of our force times the magnitude of the displacement, or distance traveled, times the cosine of theta. Regardless of whether there is friction, that would be how much work is being done by the applied force. Now let's say there is friction. If there is friction, it's acting always in the opposite direction of the motion, right? So the work done by friction would be whatever the friction force is times the distance traveled times the cosine of, well, what's the angle between the friction force and the distance, or the direction vector? 180. And the cosine of 180 is negative 1. So friction always does negative work. meaning it's always going to try to slow it down. Always, because friction is always in the opposite direction of the motion.
Is it just 180 because it's the angle compared to the...
Well, yep. So if we look at this, and we look at this angle right here, what would that angle have to be if one is to the right and the other is to the left? 180 degrees. Yep. Alrighty. Any questions so far? Yes?
Is workforce in newtons?
No. Force is in newtons.
I mean, is work, like what is the...
What are the units? Well, how do we get it? That's a good question. What are the units for force? How do we get force? I mean work, I'm sorry.
Well, you get times the...
So work equals force times displacement. What are the units for force? Newtons. And what are the units for displacement?
meters.
Meters. So often it'll be called Newton meters. Now, 1 Newton meter turns out to be the same as 1, and what we're going to call it is joule. Joules are the units for energy, which leads us directly into the work-energy theorem. The work-energy theorem says the following. Well, here, let me propose a scenario for you. So we have our horizontal surface, and we have our mass, and we apply a force. Now, if we apply a force, what do you think might very well be the resulting behavior of the object? It might accelerate. It moves. If it accelerates, what's going to change? Well, displacement's going to change, true, its position, something else. How did we originally define acceleration? Acceleration is a change in velocity. So its velocity is going to change. Right? Well, this brings us to something called kinetic energy. Kinetic energy, and I'm just going to use K for that. Your book either uses just K or KE. Let me see. It uses KE, okay. And kinetic energy, kinetic part means motion. So it's the energy of the motion of the object. And it turns out that kinetic energy is 1/2 he said, 1/2 times the mass times the velocity squared. And if an object is accelerating, let's say it's speeding up, then the velocity is going to increase, in which case the kinetic energy will increase. And the work-energy theorem says that the increase in the kinetic energy, or the change in kinetic energy, is equal to the amount of work being done. So the work being done equals the change in kinetic energy, which can be measured now in either joules or Newton meters. So that force times the distance times the cosine of the angle between those two vectors is equal to the final kinetic energy minus the initial kinetic energy. And usually, not always, but usually, in our scenarios, what that means is not the mass that changes, but the velocity. So that would be 1/2 times the mass times the final velocity squared minus the initial velocity squared. Yes?
So to find kinetic energy, we can use either equation.
I don't understand the question.
We could use the work equation and then the kinetic energy equation.
Well, if you know, let's say the object wasn't moving in the beginning. So its kinetic energy would have to be equal to 0, right? And let's say we apply a force of 30 newtons to this mass of 10 kilograms, and we drag it 10 meters. Okay? So, this new scenario, let me draw this out. So what did I say? This was 10 kilograms, right? And let's apply a force of 30 newtons. And we're going to move it 10 meters. And its initial velocity was 0 meters per second. Can you tell me what the final velocity is? Well, we could do this a couple of ways now. Before we even knew anything about work and kinetic energy, we could have done this. Because you could calculate the acceleration of the object, right? Force equals ma. So if we assume an average acceleration then of 3 meters per second squared over a distance of 10 meters with an initial velocity of 0, we can use one of our equations right up there to find out what the final velocity is. I think it would be the third one. V squared equal V initial squared plus 2a delta x. So we could answer the question that way, finding the final velocity. Or we can say, hey, wait a minute. I know the force is 30 newtons. And the displacement was 10 meters. And the angle between it is 0, so cosine of 0 is 1. And that's got to equal, well, think about it. The initial kinetic energy would be 0, so the work being put into this would have to equal just the final kinetic energy. So that equals 1/2 mv final squared. Why? Because the initial kinetic energy was 0. So when we work this out, you could actually work this around and you'd find out you'd get exactly that equation. Force equals what? ma times delta x, the distance, equals 1/2 mv squared. The mass divides out. And when you multiply both sides by 2, what do you end up with? I didn't leave myself enough space here. You end up with v squared equal 2 times a times delta x, which is exactly what you would have had with an initial velocity of 0. Right? So this is one of the places where physics gets to be really cool, because all the stuff fits together. Any other questions? Okay.